We now come to the most non-intuitive part of all of 801, and arguably perhaps the most difficult part in all of physics. And that has to do with gyroscopes. And I really urge you to pay a lot of attention and not even to miss 10 seconds. Because you're going to see some mind-boggling demonstrations which are so incredibly non-intuitive that unless you have followed the steps that lead up to it, you won't have any idea what you're looking at. It will be fun, it will be cute, but it won't do anything for you. Imagine that you and I go in outer space. No gravity, we're somewhere in outer space. And we have this bicycle wheel there. And I'm going to put a torque on this bicycle wheel in this direction. So I'm going to put my right hand towards you and my left hand away from you. And I do that for a short amount of time and I let it go. It's obvious what's going to happen. This wheel is going to spin like this forever and ever and ever. I've given it a little torque. That means if there's torque, there's a change of angular momentum. The angular momentum change must be torque times delta t. And so I do this and let it go, and it will rotate about this axis forever and ever and ever. Simple, right? Okay. Now, I'm going to torque it in this direction. So in outer space, really standing still, and all I do is do this, and I let it go. Then it will rotate forever and ever and ever and ever in this direction. That's clear. Now comes the very non-intuitive part. Now I'm going to give it a spin in your direction. And now again, I'm going to torque like this. What will now happen? You will say, or you might say, I'm not accusing you for anything, you might say, well, you give the wheel a spin, so the wheel will probably continue to spin, and you do this. So maybe what you're going to see is that it will rotate like this, as it did before, and in the same time, the wheel would be spinning. But that cannot be. Because if the wheel would be spinning like this, then the angular momentum of the spinning wheel is in this direction. And if I would give it a twist, and if it would continue to spin and it would rotate like this, then this spin angular momentum would go around like this. And that cannot be because there's no torque on the system. Because once I let go, there is no longer any torque. So it is not possible for the wheel to keep rotating, and as a result of this torque that I give it, that it simply goes around. That is not possible. How is nature going to deal with that? I'll show you that on a view graph. It's very non-intuitive what will happen. And we will then also, I will also demonstrate it to you. So here is a situation precisely as I described it to you. You are, as an observer, in this direction. This is the direction of 26-100. So you are viewing the wheels like this. They're spinning towards you. That's what I will do shortly, and that's what I implied now. This is my right hand, and this is my left hand. The separation between my right and left hand is little b. So the torque that I apply is Bf. It's this arm, so to speak, times this force. And the force is perpendicular to the arm. I apply a torque for a certain amount of time, delta t. When I do that, I add angular momentum in this direction. But the wheel was spinning in this direction, you see it. And so the angular momentum of spin of the wheel is in this direction. I add angular momentum in this direction. And you see that here. So this was originally the spin angular momentum of the wheel. I torque for a time delta t, and so I add angular momentum like this. And then I stop. So I only torque for a short amount of time and I stop. That means after I have stopped, the angular momentum of the system as a whole can no longer change because there's no torque on the system. And the only way that nature now can solve that problem is to tilt this wheel in the way I've indicated here and to make it spin in this direction, and it will stand still. In other words, I hold it in my hand, the wheel. I will get it. I give it a spin. I hold it in my hand. I spin it towards you. And I'm going to put my right hand towards you and my left hand away from you. The spin angular momentum is now in this direction. So I'm going to give it a torque like so, that means up. And what will the wheel do? The wheel will do this. It's very non-intuitive. Watch it. Isn't that strange? You wouldn't expect that. I'll do it again. So I'm going to torque by pushing my hand towards you. And the wheel does something completely unexpected. It simply tilts. If I torque the other way around, then the torque, of course, will make it flip like this. I'll give it a little bit more spin angular momentum. So now I move my left hand towards me and towards you, and my right hand towards me, and then I expect that the wheel will do this. And that's what it does. Extremely non-intuitive. These torques applied to a spinning wheel always do something that you don't expect. However, there is one thing that always helps me in terms of guiding me, and that is you can always predict that the spin angular momentum will always move in the direction of the torque, which is this external torque that I applied. Let's go over that again. We have here the spin angular momentum that you saw was pointing in this direction, and I applied a torque in this direction. It's a vector. And what does the spin angular momentum do? It goes in the direction of the torque. And then when I stop with my torque, then of course nothing changes anymore. And so what happens is this wheel tilts. But notice that L, the spin angular momentum, has moved from here to here. And I was torquing in this direction, so it moves towards the torque. If you have digested this, then you can test yourself now. Now we have the same wheel. I'm going to rotate it in exactly the same direction. But now I'm not going to torque like this in the z direction, or like this in the minus z direction. Now I'm going to do this, or I'm going to do this. Try now to really concentrate on what I just taught you. And try to give an answer to the following question. The wheel is rotating. I hold it in my hand, and I'm going to torque it like this, so that the torque vector is in your direction. Angular momentum was like this. Torque is like this. What will the angular momentum vector do? Move in the direction of the torque. What will the spin angular momentum vector then do? If the torque is in this direction, it will do this. It's going to move in the horizontal plane. Very non-intuitive, but that's what it will do. And I will show that to you. I'm going to spin this wheel. I'm going to spin it with a high angular momentum, high spin angular momentum. And then I'm going to sit on this stool, and I'm going to torque exactly as you see on the picture on the right. I'm going to torque like this. And as long as I torque it like this, that spin angular momentum wants to go around in the horizontal plane. And when I torque the other way around, it will go back in the horizontal plane. I'm going to torque exactly as you see on the picture there. You ready? I stop the torque, nothing happens. I torque backwards, I keep torquing. I keep torquing, I feel it in my hand, I really have to push. I keep torquing, and I stop torquing, and it stops. So the angular momentum vector is chasing, so to speak, the torque. Is that non-intuitive? Very non-intuitive? It's also dangerous sometimes. We call this motion of the stool, and in this case the motion of the spinning wheel, we call that precession. So you apply a torque to a spinning wheel, then what you obtain is a precession. I can show you the precession in another way, which is in fact very intriguing. Suppose I have here a string, a rope, like we have there. And I stick into that rope, I attach to the rope this wheel, just like so. And I let it go. Well, we all know it will happen. Clunk. It's clear. All right. But now I'm going to spin it before I let it go. So here at the bottom, at this point P, there's a loop. And here is the axis of rotation of the bicycle wheel, which is solid brass. It's a solid piece. And I give that a length, a little r, not to be confused with capital R, which is the radius of the bicycle wheel. So this is capital R. And it can rotate about this here reasonably freely. I call that center point Q. And let this be the part of the wheel that is on your side. I try to make you see it a little bit three-dimensionally. Suppose now I give it a spin in this direction, omega s. S stands for spin. In what direction is now the spin angular momentum? Use your hands, your thumbs. Spinning in this direction, yeah. Spinning in this direction, angular momentum is in this direction. That's a spin angular momentum. L spin. Well, there is a force on this system, mg, and that force is in this direction. It has a mass m, the bicycle wheel, and it has a radius capital R, and this part is little r. So relative to point P, there is a torque. And the torque is R times mg. This is 90 degrees. So the cross product is nice. The sine of that angle is 1. So the torque relative to point P is R times m times g. In what direction is that torque? R cross F. In what direction is that torque? Use your hands, thumbs, whatever you want. You think in this direction? I disagree. I disagree. R cross F is, you must be kidding, in the blackboard. It's not out of the blackboard, it's in the blackboard. R cross F is in the blackboard. There is a torque in this direction. Nature, gravity, provides that torque. What will the spin angular momentum do? It's going to move in the direction of the torque. It's going to chase the torque. So what will it do if the angular momentum is here? What will it do? It will do this. And as it moves, the torque will always be perpendicular to the plane, to the string, and R. You can just see that for yourself, why that is. At this very moment, when the angular momentum is like this, the torque is in the blackboard, because it's R cross F. But when I'm here, this R has changed position and always remains perpendicular to the wheel. So the torque will also change direction. And so this angular momentum, spin angular momentum, will keep chasing the torque and starts to rotate freely. That is exactly what I was doing when I was sitting on the stool, except that I had to apply that torque in my hands like this. It's exactly the same direction. I had to apply it all the time, and when I stopped, the precession stopped. Here, however, the torque will never stop, because this mg will always be there. And I will show that to you shortly. You may say, you must be crazy, because you're violating Newton's second law, F equals ma. This object got to fall. There's only one force on that object. F equals ma. How can it not? The center of mass must fall with acceleration g. Aha. There is not just one force on that object. What do you think is here? The tension in this cable, T, will be exactly mg. And so the net, the sum of all forces on that object is 0. There is no net force on that wheel, but there is a net torque. And that's why it's going to precess. If there had been a net force, then indeed it would also go down if this force were larger than this. So nature is very clever, the way that it deals with these rather difficult problems. Before I will show you this demonstration by spinning this wheel and then hanging it there in that rope, I want to mention that the angular frequency of the precession, which should never be confused with the angular frequency of spinning, is derived for you, it's only a 3 or 4 minute job, on page 344 in your book. And I will not derive it here, but what comes out of it, that it is the torque, which is the one that we have here in this case, divided by the spin angular momentum. That gives you the frequency of the precession. In our case, for our bicycle wheel, it is RmG, and the spin angular momentum of this wheel, if it is rotating with angular velocity omega of s, would be I times omega. Remember, L is I times omega of a spinning wheel. So I have here I, rotating about point Q, this is the axis of rotation, times omega of the spin. This is the spin, and this is the precession. And then the period of precession would be 2 pi divided by omega precession. Let's take a look at that equation and see whether that sort of intuitively makes sense. First of all, if you increase the torque, the upstairs, then it says that the precession frequency will increase. That makes sense to me, because the torque is persuading the angular momentum to follow it. So the torque is persuading the spin angular momentum to change. Well, if the torque is stronger, then it is more powerful, so you expect that the precession frequency will be higher. However, if the spin angular momentum is very powerful, then the spin angular momentum says, sorry, torque, I'm not going to go as fast as you want me to go. So when you increase that spin angular momentum in the wheel, it is also intuitive that the precession frequency will go down. As the wheel spins, it has spin angular momentum, but as it precesses around like this, there will also be angular momentum in this direction, because it's rotating like this. Therefore, there is a total angular momentum, which is the vectorial sum of the two. This equation will only hold